strong whale damper absorb atomic level vibrations. When I look at this, I have the first question asked, is it necessary? Why we need to do that? The short answer is no. It is not required to absorb vibration to atomic level. Nanometer level would be sufficient. It would be quite enough. The real question we want to discuss today is how long it would take to make the whale vibration decay to nanometer level, or how quickly the decay of the whale vibration. We are talking about how quickly. So absorb atomic level whale vibration would make the whale vibration decay faster. Before we go into the content page, just want to show some noise data we gather in the last 20 years, talking about the noise level, undercar noise level, against the frequency of the whale vibration. In general, for the noise radiation from the whale vibration, we normally consider from 400 Hz to 2000 Hz normally, because this is a major frequency band of noise radiation from the railway. And then if we look at how much vibration would create noise level, you could not imagine that even atomic level vibrations, it already create lowest noise level. It is around 30 to 50 dB, even at this level. And then nanometer vibration is talking about 1 nanometer to 50 nanometer. The noise level is loud, but is still acceptable. Even in the sub-micrometer level, is talking just less than 1 micron. It is still acceptable, sometimes up to 1 micron, sometimes not acceptable. But once higher than 1 micron, normally, the noise level being too loud, it will lead to mitigate. Before we go on to the detailed presentation, we have an idea how small scale of the vibration displacement it is in micrometer scale or nanometer scale. Once it is more than 1 micrometer, the noise level is too loud. Okay, the content of today's seminar. Because we just found this 2 years ago, so we would review the process, how we found it, the discovering process. We measure the noise and vibration level inside the tunnel, measure the check decay rate, and compare the check decay rate measurement with continuous excitation and impulsive excitations. Then we found that there is vibration accumulation by the Fastener reflection, and also whale damper can stop this vibration accumulation. Then we will talk about some theory. The pin-pin resonance is also due to the Fastener reflections. Damper rotor interface gap uncertainty. Because when we put a damper onto a whale, there may be some uncertainty on the surface, making there is some gap. Then we're talking about two types of whale damper. One type is rigid contact interface. The other type is profile contact interface. Two types of different whale damper. And then talking just very brief, talking about a good damper would normally consider use tune mass damping to amplify the response and amplify the dissipation. So then we will just promote the next two seminar. The next one will be the whale damper suppress corrugations by 90% on the 10th of May. And then whale damper to suppress ground bond noise as a retrofit solution for ground bond noise on 14th of June. Okay, this is the whale vibration. We conduct the measurement. We put a sensor. This sensor measures the lateral vibrations, and we put a sensor underneath the whale. And this is the damper. This damper is quite small. Actually, with a small modification, we can fit 3 damper in single space. So if the damping is not enough, we can always add more damper. The microphone is very close to the whale. So this is the noise level, vertical vibration, the sensor underneath the whale. And it has the 135 dB vibration level. And the noise level peaked at 500 Hz. The lateral vibration from this sensor, both have this peak at 500 Hz. So we design a damper to fit on it and tune to 550 Hz for both vertical and lateral. So both vertical and lateral vibration would be damped by this damper. once we put the damper, the 500 vibration level decreased by 13 dB, and at 1000 Hz, it decreased by 9 dB. Even with only tune it at the 500 Hz, the 1000 Hz is also have effect. So for the lateral vibration, that is the vibration sensor at this location, there is 17 dB reduction at 500 Hz and 13 dB reduction at 1000 Hz. So this graph is the A weighting noise level. The vibration level is also A weighting. We change it to linear weighting. So this is the A weighted vibration level, and we change it to linear, and then we can see in terms of vibration velocity, it is quite high in terms of vibration velocity. But if we convert it to the displacement, this is 1 micrometer. This is 10 micrometer. So this may be 25 micrometer. So the vibration level is, in terms of displacement, we are talking about micrometer. And also, if we only interested on the higher frequency, for example, 500 Hertz and above, it is normally around 1 micron or less than 1 micron. Before apply the damper, the vibration level is more than 1 micron. With the damper, the vibration level is already less than 1 micron. So this give you some idea of the scale. The vibration level in dB can be expressed in displacement, velocity, or acceleration. The equation is very simple. Just dB in displacement is 20 log the displacement level over the reference level. The reference level is 10 to the minus 12 meter for the displacement. So for the velocity, the dB is same 20 log V over V reference. V reference is 10 to the minus 9 meter per second. For the acceleration is similar. We should notice that for displacement, we use picometer as the reference. For velocity, we use nanometer. For acceleration, we use micrometer. So they are different. This is the practice of the acoustic industry. Then we talk about how to convert the velocity to displacement. If there is a vibration velocity, we just divide it by 2 pi f, then we will get the displacement. So for example, for 500 Hertz, 2 pi f 3100. So once we change the velocity to displacement, the engineering unit already divided by 3000. For example, there was 1 millimeter per second. In the vibration level, it was very high, but in displacement, it is only talking about 0.32 micrometer. Okay, then we come back to the measurement data. Okay, this is the time history without damper, the vibration time history. This is the wave vibration level, and then this is the time. The train coming, and then like this. For the 500 Hertz, the vibration level is keep at high level for the entire train pass. For the 1000 Hertz, we can see there is some peak and trough. What does this peak and trough mean? Let us see more data. This is the vibration level with damper. We can see that once we apply the damper, variations is much large. This variation is according to the location of the bogie. At the location of bogie, the vibration is very high. In between the bogie, at the middle of the train, the vibration is very low. So once with the damper, it stops the vibration propagate from one bogie to another bogie because it decayed in the middle. So in other words, the wave damper is making the wave vibration being localized, stop the vibration accumulation from multiple wheels. Without the damper, the vibration is kept at high level for the entire train pass by. But with the damper, the vibration is only at the wheel location. Once the wheel moving away, the both moving away, the vibration level decay a lot. We can see that in the middle of the train, the vibration is very low in the middle of the train. So if a wheel has a wheel damper, you sitting at the middle of the train would be much quieter than sitting close to the wheel. But without damper, they are similar. Without damper, the red line is without damper, they are similar. Once with the damper, the blue line is with damper, it is reduced the vibration a lot. Okay, this is all the data we are going to present today. So it is too complicated. We will make it show it one by one. Okay, showing the pass by vibration time is at 500 Hz with and without damper. Without damper, the FH vibration level, LEQ, low damper, is 138. Once put the damper, the FH vibration level, LEQ, is 155.6. We should notice that this FH line is more close to the top because it's energy FH. So the damper reduces 13 dB at 500 Hz. If we look at the trough level, so look at the locations in the middle of the train car, then this is the trough level. It is around 127 dB. And with the damper, the trough level is 96 dB. The reduction is much better than 13 dB, is 31 dB. So then we look at the displacement. We're using the formula to convert the vibration velocity into the displacement. We found that we are talking about micrometer vibrations down to 20 nanometer vibration. So once with the damper, we can reduce the trough vibration level to 20 nanometer. Also, it very quickly to achieve the background vibration. The background vibration is less than 1 nanometer, a few atomic size vibration with the damper. So we can see the difference. Without the damper, the decay is very slow. With the damper, the decay is very quick. So we look at the decay. Then we measure the check decay rate using the standard method, using a hammer with multiple sensors. We found that the check decay rate is 1.8 dB per meter. And then with the damper, it improved to 5 dB per meter. Although it looks very good, the decay is very quickly, but we still not achieve the TSI target 6 dB per meter. Our damper may have some strange effects such that the check decay rate measurement did not measure the decay damping dissipation by this damper. So very good decay, but only 5 dB per meter. We just take the data or the first vibration sensor and hammer on the midspan. Then the first midspan, we put a sensor to see how the vibration change. This is the impact. It look like same. The red line is without damper. The blue line with damper. Both so very quickly decay. This is only take half second, less than half second to decay. So we enlarge this half second. We can see some difference. Enlarge this half second. We can see that even for the red line, it decay 30 dB, then there is some refractions. The green line is the decay with damper. The red line is without damper. This is the time. So it takes 50 milliseconds decay from here to there, 50. But we can see that they have the similar slope with damper or without damper. They have similar slope. The difference is there is some fluctuations without damper. With damper, this fluctuation is minimized. So what is this fluctuation? Why the damper reduce this fluctuation? We further investigate. We found that this is the vibration reflection from the fastener. It is less than 0.1% of the original vibration impulse energy. But it still create ripples. These ripples making the decay very slow. With the damper, it make very quick decay and almost no reflection. Without damper, the decay is 15 dB, then there is some fluctuation. With damper, we have a very deep decay, 50 dB decay without reflection until there. Okay, that was 500 Hz. If we look at 1000 Hz, they are similar. The trough level is reduced from 109 to 79, 30 dB reduction on the trough level. The displacement is from 45 nanometer reduced to 1.4 nanometer. We also conduct the check decay rate. In this case, the check decay rate with and without damper do not change much. So we also enlarge this half second between 14 and 15 seconds. We can see that the first decay without damper, the brown line, there is some refractions, some fluctuation. With the damper, it strictly decay 50 meter, 60 meter without fluctuation. So there is also some reflection from the fastener. What I mean reflection is when we hit the whale there, the wave will propagate along the whale. Whenever it comes to the fastener, there is some small reflection coming back, some small reflection coming back, small reflection coming back. These small reflection, however, are all in phase. They are in phase reflection. So such that although the vibration is small, but it is many and they are in phase. We are going to see how this is going to be the in phase reflection. Okay, this is the most difficult slide in the presentation. We make it just last a few hours ago to try to demonstrate some vibration propagation. This is the whale with fastener base plate at 0.625 meter. That is normal in Hong Kong. Around 0.6 to quite normal all around the world for all the new whale, they are around 0.6 to 0.63 meter slipper spacing. When we put an impact vibration there, the impact vibration would travel on this way, on the right side and on the left side. If we put a different time, we can show this graph. We use T. T is representing the time for traveling to space. So when the time past T time, it would be 2 base pair going to this location. This location is the wave travel at this impact. And then the wave at T time, this is the wave is traveling to this location. So at every T, it will travel 2 base pair. So this is the wave just propagate out. But whenever it passing through the fastener, there would be reflection. There would be reflection. So this is the reflection. It travel this fastener, across this fastener, there is some reflection. And this is also reflection. And by the way, this two reflection is in phase at the middle. And then this is also in phase there. This is also in phase there. So this in phase reflection is at the time interval of t, time interval of the time to traveling to space. This figure is just made a few hours ago. I hope this can explain how the fastener reflect the wave vibration and being in phase. And more vibration and more reflection and more reflection. This is just too complicated. So we believe those vibrations, the accumulation of vibration, the in-phase vibration accumulate, creating these bubbles. The first impulse there, and then there is some vibration reflection from the fastener. And the whale damper stop this vibration. And this reflection is very small scale. With two wheels, in Hong Kong, many trains have the wheelbase of 2.5 meter between two wheel set. This is exactly 4 times of the slipper spacing. So they also create in-phase vibration. Okay, then we talk about the 2 types of whale dampers. One type is rigid contact. We're using metal contact to the whale. So make sure there is no gap, because metal contact to metal is being in contact, rigidly contact. Different type of damper. Another type of damper is profile contact. Normally, they have a rubber layer at the interface. Most of the damper using this design idea. The interface, this profile interface, is designed to maximize the contact area to enhance the viscoelastic damping. There may be some partial contact interface because when we put the damper there is some gap. It do not totally match the whale, especially there is rusting on the whale. So there is partial contact interface, and this partial contact interface would affect the damper performance. It also provides vibration isolations between the whale and the damper, such that whale vibration energy does not transmit to the damper. This is profile contact wheel damper. They need to make the damper very close fit to the wheel surface. This is type of widget contact. Widget contact is designed to maximize the contact rigidity. So the contact is very rigid. Make sure it widget contact to ensure effective transmission of damping force, and also make sure the tool mass damping. In the profile contact, they put the rubber layer at the contact area, but for the widget contact, the rubber layer need to put somewhere else. So for example, the rubber layer in this one is putting at the vertical surface, a very flat surface between this cylinder and this flat mounting plate. So there is a very flat space for the rubber to mount on it. So a close-up on these two type of damper. So the widget contact with point contact, in this one is 3-point contact. Make sure it fit well. And the rubber layer is in between this plate and the cylinder. In this one is they have the metal inside the rubber to perform the tool mass damping. So the wheel damper normally would use tool mass damping to enhance the dissipation. All the wheel damper use viscoelastic damping, but it is spot bend, but not strong. Many damper, they would include the tool mass damping to amplify the hysteresis energy dissipation. They are strong but narrow band. Also, to control the tool mass damping is we need to control the stiffness, the effective stiffness of the rubber layer. So if we want to have a very strong TMD, normally we need to have very rigid mounting in order to control the effective stiffness. When the wheel vibration propagate along the wheel, the energy would be dissipated if there is something touch on it. So the profile contact is try to fit damper to touching the entire wheel surface. So whenever it propagates, the vibration energy will be transmitted into damper like this. The vibration would be transmitted into the rubber as long as there is a very good fit profile fitting. But in reality, such as this one, we can see there is gap. This gap, even in the micrometer size or nanometer size, it would affect the damper performance. On the other hand, the widget contact, this process makes sure they are always widget contact with 3-point contact. They provide a very high clamping force such that even the atomic scale vibration can be absorbed. Once we fit the damper on it, the TMD would be amplify the oscillation and dissipate the energy in this rubber layer. Okay, it's come to the end of the webinar. Just looking at this graph again, it shows that we need to control the vibrations below this level. So we need to control the vibrations below 1 micrometer and make it very quick decay to nanometer scale. This is the last slide of the seminar. You are welcome to discuss any point. So just let me put a 4-point summary. Micrometer wave vibration at high frequency is too loud. We need to control it. And the vibration control at nanometer level is required. Absorb atomic scale vibration, make the wheel vibration decay faster. We need this to make a quiet wheel. We need to make a very fast decay damper to decay the wheel. Wheel damper can stop accumulations of atomic level vibration, and its interface gap, even less than micrometer, affects the performance significantly. Check decay rate, in our experience, check decay rate may not reflect the actual damping performance. In some cases, we don't understand this. We will further investigate on this point. Vibration accumulation by fastener construct the pin-pin resonance and affect the wheel vibration decay. I will hand over the time for Max, and you are welcome to have any questions. Thank you for your time. Thank you very much.